Good evening. I am Sourav Mishra, a PhD student at the Artificial Intelligence and Robotics Laboratory, Indian Institute of Science, Bangalore. I am pursuing my PhD under the guidance of Professor Suresh Sundaram, who also heads the AIRL lab. At AIRL lab, we work on robotics, reinforcement learning, computer vision, and controls. My research interests are continual learning, multi-level learning, and physics-informed neural networks. I am grateful to IEEE ICAST for accepting our work, React, Rational Exponential Activation for better learning and generalization of pins, and giving us an opportunity to present it. This is a brief outline of the presentation. We will start with the introduction and look at the mechanics of pins. Then we will review key relevant works from recent literature. Next, we introduce React and the experimental settings. Thereafter, we will discuss the results and conclude the presentation with key findings and directions for future research. There are two major ways of simulating the behavior of physical systems: data driven and numerical. In data driven methods, we start with no prior knowledge of the system and try to infer its behavior by collecting lots of data. Whereas in numerical methods, we usually start with a prior model and limited data. We evolve the available data as time passes according to the model. However, acquiring high quality and quantity of data becomes an expensive task, and at the same time, numerical methods are computationally intensive. In this context, pins provide a middle ground by integrating limited data and physics information to simulate a system to an acceptable level relatively fast. Pin learning involves optimizing several loss functions together as enlisted on the right. The pin output must satisfy the physics and the imposed boundary and initial conditions, and must also adhere to the collected experimental data. These conditions are imposed by the loss functions. In the figure below, we can see that a purely data-driven simulation of a simple underdamped pendulum fails to predict the system behavior after the training interval, whereas upon the inclusion of physical constraints into the training objective, the model is able to perform considerably better even beyond the time for which the system was observed. As mentioned in the previous slide, pin optimization involves several objectives, which makes it a challenging problem. It is difficult to satisfy all the constraints at all times. Also, selection of activation functions for pins is not as straightforward as for typical deep learning problems. In pins, the system dynamics plays a key role in selecting a suitable activation function. So we do not have a one activation fits all for pins like we have ReLU for deep learning problems. Few desirable properties of activation functions for pins are enlisted here. In the literature, several adaptive activations for pins have been proposed, and we highlight two key ones here: self-scalable tanh and adaptive blending units. We see that self-scalable tanh has saturation regions only for beta is equals to 0 and takes on a limited set of shapes. Similarly, ABUs are limited by the pre-selected set of activations as well as the convex combination through softmax. Neuron-wise adaptive activations have also been proposed in the literature, but they increase the model size quite a bit. Recently, adaptive activations have also replaced normalization layers in transformers. To address the limitations of ABU and STAN, we propose React, a rational exponential activation with four learnable parameters a, b, c, and d. Its shape for different parameter values are shown in this figure. Depending on the values, it can take unbounded outputs and have saturation regions, while maintaining differentiability. The adaptive nature of its saturation regions enables React to suppress noise in a controllable manner, which leads to better parameter estimation from noisy data in inverse problems. We will see this in the forthcoming slides. The experimental settings for forward problems and the performance evaluation metrics are shown here. React outperforms all other activations for the problems considered, showing maximum improvements on the heat problem with 3 orders of magnitude decrease in MSE. It also generalizes well beyond its training time interval, as seen by its performance on Alenkern diffusion and Burger's equations. The viewer can find these results in Table 2 of our paper. Here, we show the performance on Alenkern, Burgers, and diffusion equations. These values are normalized by using tanh as a baseline, and some activations with large negative relative performance values have been removed for better visualization. React performs better in all these cases. In this slide, we examine the performance of React on inverse problems. Table 5 shows the performance comparison with S-tan and ABU for different levels of noise standard deviation values. We add Gaussian noise with zero mean and the mentioned standard deviation to simulate realistic experimental data for parameter estimation. We consider thermal diffusivity and wave velocity estimation problems. Table 4 shows the percentage error in parameter estimation across all the activation functions considered in this study. These tables show the effectiveness of React in inverse problems as well as its robustness to noise in the experimental data. We considered the three functions shown above to evaluate React's performance in function approximation tasks. In the plot shown on the right, the values are normalized with respect to tanh and activation functions with large negative relative performance values have been removed to make the visualization better. The results clearly show React's ability to approximate complicated functions better than other activations. The viewer can find these results in Table 3 of the paper. In this work, we developed a novel adaptive activation function called React for pins and showed its effectiveness across a wide range of tasks, forward problems, inverse problems, and function approximation. React outperforms existing activations and the state-of-the-art adaptive activations in these problems. In future work, we will extend React to more classical deep learning problems such as classification, object detection, etc. This brings me to the end of my presentation. Thank you for making it to the end. Have a great day ahead, and if you have any questions, I will take them now.